7 to 8, completely voluntary. If you are on top of things, don't waste time to come in. All right, if you have questions, the homework that you haven't been able to understand, and you haven't made use of Mike's office hour, then show up. I will tell you on Tuesday where the help session will be. In addition to that, Mike will make an attempt to have additional office hour on Wednesday of next week. The test is at 7, so just in case for those of you who have the habit of studying at the last minute, right? So agenda, I want to finish up rental transport equation, mainly looking at the physical interpretation of the momentum equation. We've done that pretty well for the continuity. I want to revisit continuity, use it as a springboard to look at how one can use plain, simple English to describe in layman terms what is it in the momentum equation. And on that front, we will also touch on the equation. It's called angular momentum. We won't use it, but at least you should know about it. And the fourth equation in that rental transport is the energy equation, which we will defer until a month later. Beyond that, I want to just spend time on homework that are due today, so please upload that. Oh, sorry, I take that back. There will be a quiz today, so let me pass that out. So don't turn in the homework online, because it will not be graded. There's upside down quiz that I will give you plenty of time at the end of today's lecture. Maybe 5, at most 10 minutes. It's a walk in the park. If you have done your homework, this is a gimme. And then I will touch on the new homework, nothing substantial, very manageable homework. And then I will spend half the lecture on validity, focusing on application and the concept of what we call stagnation pressure. Some of you know it, some of you don't. But the homework for next Tuesday has to do with that concept. So I want to make sure we're all on the same page. If I have time, I will dive into the derivation of the Bernoulli equation. It's all to you to ask me questions, to slow me down. On the assignment, the last reading before test 1 is still on Bernoulli, and homework is 2 hours, 3 problems. And that's all you're responsible for, including a lecture on Tuesday. Of which, as I told you, I spent a little time doing a quick review, 10 minutes at most, and then I open myself for any question you have for preparation for test 1, so all homework, anything. Derivation, reading, just prepare. If you have no question, I will continue to lecture. And everything I lecture on Tuesday will be responsible for the test. Questions before I move on? Yes?
Will there be no homework due next week?
I'm sorry?
Will there be no homework due next?
There'll be no homework next Thursday. You need a break. So there'll be a test on Wednesday evening. We'll have lecture as regular on Thursday, but no homework to be due on Thursday. The next homework assignment after test 1 will be due the following Tuesday. Fair enough? It'll still be a busy week. It'll still be a very intense week. So, rental transport theorem, we have done that for the continuity equation. The simplest form of the continuity equation, not in this vector and nomenclature type formulation. If I were to rewrite that, so that I can use that to help read. So the bottom line is trying to learn how to read those equations to a non-engineer. And we have done that for continuities several times, so I'm not going to spend a lot of time on this. So the time derivative term is rate of change, or what? Mass in the control model, very good. No more, no less. This is very particular. And if you miss something, you won't get full credit. Instead of just rate of change, I can even be a little bit more specific. It's actually the increase going up. And that will have some bearing later on when I go to momentum. Why? Because the subsequent term represent the mass, flow, weight, out. This is very important, of my control volume. And the last term is the mass flow rate in. And because of that sign, because of that difference, out minus in, you have to think about this to appreciate the sign. Because of that difference, and think about the diagram on the left, flow rate out at the base, flow rate in at the top. The out minus in represent the term here being increasing mass flow in my control volume. I know it's not easy to comprehend that in the lecture, but maybe you have to think about this more detail at home. Or it may be easier if I flip the term to the other side of the equation, but I want to leave it this way so that I can use it as a springboard for momentum equation. So let me pause and make sure you understand how the sign come about. I think you can read it, we've done it before, we didn't pay attention to the sign, but now it really comes to bear. And this increase is a consequence of the last two terms in terms of the sign. Do you get it? If you don't worry, just sit on it at home and think it through, change the term, put it in a different side of the equation, you will click. Yes?
So just in terms of convention, we could switch the in and the out and make it the change, or the change in the decrease of the volume of the tank?
Yes, in a way, yes. You can play with the sign, you can put the term, take it on the other side of the equation, and for that aspect, it's probably easier to visualize that if you do that. But I'm keeping it this form simply for the reason I have to use this same form for momentum equation. You're absolutely right. It will be much easier if I flip the sign and look at everything in terms of positive light. Yes?
Can you talk about what B and beta are real quick in the
Sure. So the random transport equation is a very abstract, simple equation which is the basis of the homework you did way back in chapter 4, where I have a control volume that coincides with my system at the same time. And I have flow coming in here, flow coming in here, and flow go out. All right, and I don't look at what is it that I'm trying to analyze. It could be energy, it could be momentum, it could be mass of all those quantities into my control volume and leaving my control volume, and at the same time that's coincide with my system. Right? A moment later, a tenth of a second later, things change. The system mass going out, system mass coming in, based on whatever velocity they were at, respectively. And the random transport equation, in the general form of this capital B and small beta, which is per unit mass, is a general attempt to bookkeep how much come in, how much go out, and how do I use my physical equation, constituent equation of system conservation of mass, system conservation of momentum, system conservation of energy, and transform them from system via this cartoon to my random transport equation for a control volume. So that in a nutshell is what's come out of this equation. Now I can answer the question. So B can be as you want. Anything of those quantities I mentioned before. Momentum, mass, energy, angular momentum. And when you do that, then the beta will have to change correspondingly for each of the quantity, but per unit mass. All right? And you've seen what we have done for continuity. We let capital B be the mass, and beta become 1. And you've seen what we did with momentum. Capital B is the linear momentum, mass times velocity, and beta is our momentum flux, so on and so forth. And then momentarily we're going to do angular momentum, and beta will take on a different form. A month later, we're going to do beta in terms of energy, and then will come the energy equation. Does that help? Other question on the general Reynolds transport equation? So when it's done, how the continuity equation, where is looking at the tank, the balance of how much mass increases in my tank, must balance it by the difference of the outgoing mass flow rate and the incoming mass flow rate, so that everything equal to 0. I cannot create and destroy mass. That's the system equation. Now this is the equivalent control volume equation. Do you get it? Okay, so now I want to revisit the momentum equation. And with that, I want you to help me to read that in plain, simple English. So the Reynolds transport equation for momentum is a little bit more daunting. Instead of 0, I have forces now. Do you see that? So, question. This dot product with integral, so on and so forth, is a little bit daunting for me. Can you replace that with something that you're more comfortable with? Just this term. Or, if I go back to the Reynolds transport equation, what is this term in a more familiar nomenclature? Say that again? Close. Close. Mass. It's mass but not mass. Mass flow rate, thank you. I have to be very particular. If you say mass in the test, you will only get partial credit, if at all, because it's not mass. It's rho VA. This is my m dot. Likewise, despite all this dot product, integral, differential, this is nothing but my rho VA. Do you see that? So our goal with all this as a backdrop is to try to read this equation in plain, simple English. That's what we're trying to do. It's not as transparent in this formulation, so I would like to remind you of the X momentum equation that you have seen before, and we're going to use that to try to do a physical interpretation, just like we did for continuity. So I'm simplifying my momentum equation from Reynolds transport theorem to a form that you have done many homework problems with. That look familiar? That form in a steady formulation is what you use to solve all the homework problems, all of which in the X direction. So now I'm coming to the punchline. I need you to read this equation to me in layman terms, in plain, simple English. And like I did with continuity, it may be instrumental to look at this jet problem giving a plate, to just help you anchor what each one of the terms represent and how to put it down in layman terms. Starting from the force on the left, the net force, just like you did with system, the net force, which in fluid consists of 3 categories, right? Repeat that for me, which 3? Body force, anchoring force or external force, either one, usually the unknown we're trying to solve. And then the third is surface forces with an S, which had two components. Which two? Friction and pressure. Very good. Okay. So this is my driving potential. This force has to be there to change on the right hand side something. What's that something? Starting with the easier term first. What is m dot u? What do we call that? Momentum flux. Very good. And it's in the x direction. So flux is simply a term that we invented to call m dot, mass flow rate times the velocity, and it's in the x direction. And that represents, just like in continuity, the out, leaving, out momentum flux. All right, so you can draw a parallel now between what I'm doing in momentum versus what I'm doing in continuity. Okay? The last term, same thing, but it's minus, just like I have for continuity. And it's accounting for the incoming quantity. For continuity, it's incoming mass flow rate. For momentum, it's x momentum flux, but coming in with the sign of minus. So way back, maybe 2 or 3 lectures ago, someone asked me, why do we have the sign for momentum as such, whereby plus momentum flux is out, in momentum flux is minus, or because of the formulation of Reynolds transport equation. And if you can understand the sign for continuity, you are able to understand the sign for momentum. And it's a driving potential of force that resulted in a change in momentum being bookkept with the appropriate sign as such. No more, no less. Yes?
What does the CS mean on the second hand row?
Very good. So what is CV? What is CS? Control surface. So we are looking at things only at the surface of the control wall. We call that control surfaces. Anything inside, if it's steady, I don't care. I don't even want to look at it. Right? You have just one problem that is unsteady. That's the air tank. Questions? I'm leaving this term to be the last. Yes?
Could you explain again what the first term is in the momentum equation?
This one?
The
Oh, this one?
Yeah.
Yeah, I'm waiting. I'm waiting for the punchline. So I think most of you can read these, because I've done it before. This is where it got tricky. And for that, I want you to go back to this problem, and you would hopefully infer that this is also resemblant or look similar to what I did in the continuity equation. So I would go so far to say this will represent if it's unsteady, if this jet is not steady but is changing in time, it also represents an increase. What is that question? That's all I spent the last 10 minutes on, or 20. What, can you fill in the missing blank? Yes?
Is it momentum?
That's 50%. If you want to get 100, be more specific. X momentum. Do you get it? Do you get it? So let me stop and make sure you comprehend what we have done. So just simply doing problem is good, but it will be even better if you can understand the physics. Do you see it? Do you see all the pieces, how it all fit together? So can you read the y momentum equation for me? This is x, right? X. Can you do the y momentum equation for me? What will be F? Y. What momentum? Y. Y and Y. And in real life, problem is in 3D. So you have a Z equation, which we will do at the end of the semester. And then you will have Fz, C momentum, all the way through. But the sign Y out is plus, Y in is minus, is all being referred to from the continuity equation. If you understand this, you will convince yourself that the sign is what it is. No more, no less. Do you get it? Yes?
So the sum of the forces is set equal to 0, is correct?
No. This is very dangerous. There is no. The sum of the forces is not equal to 0. This is not like here.
Okay.
Sum of the forces is only equal to the change of all of this on the right-hand side. And it's not, I repeat, it is not 0. If you do this, I'll blow your head off. And every year, there will be a handful of you do that. And to do that in the test, that means you have done all your homework wrong. And I have no mercy on you. Right? I'm joking, but it's not 0. Okay?
So
Yes?
what, I guess, like, let's say, how do you calculate it, but like,
Well, calculate the forces.
what's the difference between the x, like the difference in the x momentum flux and the rate of change? Like, what else could affect that?
Only when the flow is unsteady. If they are steady, like we did for continuity, this term is 0. This term is 0. And that's all the problem we have been doing for the entire semester and will continue.
Okay.
Right? Anytime it's a steady problem, starting from random transport, forget this. Forget this. And forget this. Okay?
Okay.
So I'm doing this, there will be no homework, and then no problem in the test that will involve unsteady momentum, but I'm just doing it so that when you go to industry, you don't panic if you have an unsteady problem and say, I don't know how to deal with that. Right? And if you have a 3D problem in industry, when you go to a co-op or summer intern, you need to look beyond what we have done here. Yes?
Can you explain again why that term is indicating that it goes up?
Oh, yeah, good. That's a very fair question. So if you ask me,